In this video, we will take a qualitative perspective of acidity and basicity. This just means that we won't be using the pK values to help us predict if something is more acidic or more basic than something else, but rather we will use a general guideline to help us determine these trends. In this approach, we will focus primarily on the conjugate base of your acid. And the more effective the conjugate base can stabilize the negative charge, then the more product will be favored and therefore the stronger the acid. Why is that? So remember, if the conjugate base A minus here can stabilize that negative charge, it will not react with the hydronium ion. So it will stay as a product, favoring the product side. However, if the conjugate base is very unstable, aka very reactive, then it will react with the hydronium ion, making the reaction go in the reverse direction, therefore having more reactants. Therefore, HA is a weak acid. So ultimately, we will pay special attention to the stability of the conjugate base A minus. And we will look at 4 qualities to help us judge this. And conveniently, there's an acronym for it. That acronym is ARIO. I like to say ARIO, and it is listed in order of importance. Well, A is more important than R, more important than I, more important than O in most cases. So A here stands for atom, R here stands for resonance, I is induction, and O is orbital. Each of these 4 factors will help us determine how stable our conjugate base is. So let's go through them one at a time. The most important factor, whether your conjugate base is stable or not, depends on the atom that is receiving that negative charge. So if you are comparing between 2 atoms to see which one is more stable, the first thing you want to see is if the 2 atoms receiving the negative charge are on the same row, the more electronegative atom will have more stabilization. This makes sense, right? The more electronegative atom, because it likes electrons more, is happy to accommodate that negative charge from more electrons. So remember the trends of electronegativity going across a periodic table. As you go from left to right, you are increasing in electronegativity. So the atoms further on the right that's receiving the negative charge will be the more stable conjugate base, so therefore the stronger acid. A different effect dominates when the atoms receiving the negative charges are on the same column. Now electronegativity will not play a strong role anymore. Rather, it is the size of your atom. The larger the atom is, the better it is to stabilize that negative charge. It can distribute it around because it has more space now to distribute the negative charge. Let's go ahead and take a look at some examples. So we're going to go ahead and compare an alkane to an alcohol. Which one of these would have the more acidic proton? Remember, in the alkane, the only source of proton you have are the hydrogens connected to the carbon, and they are all equivalent, so we just choose one to compare. So again, in order to use ARIO, we need to consider the conjugate base and how that conjugate base is stabilized. Okay, so in the alkane, notice that the negative charge is on that carbon, whereas in our alcohol, the negative charge is on the oxygen. Carbon and oxygen are on the same row, so we can use the first guideline there to determine which one has more stabilization. Oxygen is more to the right, so it's more electronegative than carbon. So oxygen is better at stabilizing that negative charge. So therefore, between these 2 molecules, alcohol will be the stronger acid. And you can corroborate this with remembering the pKa. The typical pKa of the alcohol is about 15, whereas the typical pKa of an alkane is around 50. So alcohol indeed is the stronger acid. Let's take a look at another example, this time comparing H2O versus H2S. Again, so let's take a look at how stable the conjugate base is. This time, oxygen and sulfur are not on the same row, but they are on the same column. And which one is a larger atom? The lower you go on the periodic table, the larger the atom is, right? So it turns out sulfur is much better at stabilizing that negative charge than oxygen because it is a larger atom. Again, we can confirm this because we know a thiol has approximate pKa around 10, whereas water has approximate pKa around 15. So the sulfide here will be the stronger acid. All right, so now let's move on to our second factor here, and it is resonance. If the negative charge is on a structure that can have resonance, will this stabilize or destabilize the molecule? If you get stabilized, then you are going in the right direction. Remember, resonance will spread out your negative charge. Whenever you can spread out that negative charge, just like the size example we just did, sulfur is larger than oxygen, so it can distribute more of that negative charge around. The same thing, if you have resonance, you can distribute your negative charge around more, therefore stabilizing that negative charge. Let's take a look at an example of this. Compare between an alcohol and an acetic acid here. Again, we can see the conjugate base of that alcohol is this alkoxide ion, where that negative charge is fixed on that oxygen. And the conjugate base of the acetic acid also has a negative charge on an oxygen. So here you see that atoms will not help us out here since it is the same atom. What the acetate ion has, however, is that it can do resonance. Notice you have an allylic lone pair. So it can distribute that negative charge onto the other oxygen. Remember that we call that this negative charge is being delocalized. And delocalization or resonance will give you stabilization. Therefore, acetic acid is your stronger acid. Again, this was true because as from our memory, pKa of acetic acid is around 5 and the pKa of alcohol, again, is around 15. Okay, so let's go ahead and do some practice problems with these two factors that we talked about, atoms and resonance. Let's take a look at this molecule, and I've highlighted 2 protons here. Can you tell me which proton is more acidic? Remember to draw the conjugate base in order to compare them. I'm going to change the color of one to make it easier for us to see. So let's draw the conjugate base one at a time. First with the green. So that's what the conjugate base would look like if you deprotonated that proton versus if you deprotonated the red proton. Which one of these would be more stabilized? They both have a negative charge on the carbon, so atom is not going to help us, right? So we're going to go ahead and rely on the next one, resonance. Which one of these conjugate bases has a resonance? Notice that the red structure is an allylic lone pair, right? Which can be involved in resonance. So therefore, it is the more stabilized conjugate base. So it would be the more acidic proton. Let's take a look at another example. Let's take a look at this molecule and compare these 2 protons. Notice again that if you deprotonate either of these protons, the negative charge will be on a nitrogen. So again, atoms is not going to help us here, but we might see if one has a resonance structure. Let's go ahead and draw in what would happen if they are deprotonated. Which one of these negative charges can be resonance stabilized? Yes, hopefully you can see that the green proton will be able to be resonance stabilized because it is allylic to that aromatic system. So therefore, it would be the more acidic proton. Let's continue with another one here. All right, this time let's focus on this hydrogen and this hydrogen. Which one of these hydrogens would be more acidic? Give you a moment to think about this. So if that red hydrogen is deprotonated, this is your conjugate base. Whereas if the green hydrogen was deprotonated, this would be your conjugate base. All right, so which one is better at stabilizing? Hopefully you said the red structure is more stabilized. That's because the negative charge is on oxygen, which is better than in the green structure where the negative charge is on a carbon. In fact, we are using the atoms effect here. All right, let's do one more before we go on. Let's take a look at this case. Again, I'm going to highlight the different protons in different colors so we can compare them. Okay, which one of these is more acidic? So as always, let's consider the conjugate base. If you take away the proton, where would the negative charge be? All right, so notice that both of these negative charges are on an oxygen, so atoms is not going to help us. So let's go to resonance. Did you notice that both of these will have a resonance structure? So let's see what that looks like. First, for this red case, it is again allylic to this aromatic ring here, so it can push the negative charge onto that pi bond. And in fact, it can continually have resonance around the entire ring, right? It can keep on going. So it has 3 resonance structures. Let's erase up here for some space. Okay, so that's what happens when the red proton is deprotonated. What about the green? Remember we said it is also allylic to a pi bond, so it can also be involved in resonance. Okay. All right, so we stuck here. They both have resonance. How are we to determine which one is the more acidic? It turns out not all resonance structures are created equal, right? The green structure has better resonance stabilization. Why? Because your negative charge is spread around to a more electronegative atom. It is spread to the oxygen, whereas the red structure, the negative charge is spread to the carbon, and carbon is not as electronegative, so it doesn't really like to receive that negative charge as much as oxygen. So in this case, even though the red structure has more resonance structures, it is less effective. So it turns out quality is better than quantity in this case, making this conjugate base more stable, therefore the acid more acidic. All right, let's now move on to our third factor here, which is induction. And induction is basically pulling electron density from afar. So the more electronegative a group is, it will pull the electron density towards itself more, and therefore stabilizing that negative charge. And the induction effects really depends on the number of that electronegative group, the distance, and the degree of that electronegativity. So the more electronegative the group is, the more induction effect it has. Let's see a couple of molecules here to illustrate this point. So as the basis of our comparison, we'll take a look at acetic acid. The exact pK is about 4.8. Now take a look at what happens if you add chlorine, an electronegative atom, to this molecule. Because of the induction effect, it will stabilize that negative charge when the proton is abstracted, drawing down the pKa to be about 2.9, a little bit more acidic than acetic acid. Let's take a look at a different molecule here. Remember we talked about that distance effect? What happens if we put one more carbon in between before that chlorine is attached? So it's one atom removed. How much of an effect does this have? It turns out pretty big. The pK jumps back up to 4.4, very similar to the original acid. So that was the distance effect. Now let's take a look at the numbers effect. As you can imagine, if you have one chlorine there, it has an induction effect. If you add more chlorine, more electronegative groups, what would happen? It would be a more acidic molecule, no? And indeed that is true. The pK of this molecule is about 0.7. So very, very acidic indeed. And lastly, let's take a look at that electronegativity effect. Can we put a more electronegative atom on this molecule other than chlorine? Which atom is more electronegative than chlorine? Hopefully you remember fluorine in your electronegativity trend. Right, so if you put 3 fluorine on this, the pK goes down even further. It goes down to negative 0.2. Okay, so this is the induction effect. Our last factor here is orbitals. To start us thinking about orbitals, are negative charges more stable on an s orbital or a p orbital, do you think? It turns out the s orbitals are better at stabilizing that negative charge because remember an s orbital is a spherical orbital. If your electrons are in there, it's closer to the nucleus, which is a positive charge. So that negative and positive interaction. Whereas a p orbital, the electrons will be further away from the nucleus. But we really want to think in terms of hybridized orbitals now. And in particular, remember we have the sp orbital, the sp2 orbital, and the sp3 orbitals. So the more s character your orbital has, the more it can stabilize that negative charge. So among these 3 hybridized orbitals, which one can stabilize that negative charge more? Which one has more s character? It would be the sp, right? Because it has 50% s character. And the sp2 would also have greater stabilization than the sp3 orbitals. We can illustrate this point. We can compare the acidity of the alkane, and the alkyne.
right? So if we took away a proton from each of these molecules, what would its conjugate base be? So in this case, the negative charge are all on a carbon atom, so atoms is not going to help us. There's no resonance, and there's no real induction effect. So the only thing that separates these three molecules is the orbitals in which the negative charges are on. And in the alkane case, the negative charge is on an sp3 hybridized orbital, right? And in alkene, it is an sp2, and on the alkyne, it is an sp orbital. So again, the sp orbital is better at stabilizing that negative charge, so therefore the alkyne is going to be your most acidic molecule, whereas your alkane will be your least acidic. And again, this tracks well with our previous notion from the pKa. The alkyne pKa would be around 25. The alkene pKa will be around 45. And the alkane pKa would be around 50. So alkyne at 25 is indeed your most acidic proton.
Remember though that ARIO is just a basic guideline to help us predict, and the key word here is prediction, right? It only helps us predict the relative acidity of compounds. It is not 100% accurate.
So let me give you an example of when ARIO does not work. Let's say you're comparing this alkyne with this amine. Based on ARIO, we would draw the conjugate base, and we see that the negative charge residing on a nitrogen is better than a negative charge residing on the carbon, right? Because nitrogen is more electronegative than carbon. We're using the Adams effect, the first factor there. So we would say then the amine would be the more acidic molecule. And as it turns out, this is not true because as we remembered, the pK of an amine is around 40, whereas the pK of an alkyne is around 25. So alkynes are much more acidic. All right, so again, ARIO does not work all the time, but it generally will be useful for us. But know that it is not perfect. So that rounds up our discussion on ARIO and using ARIO to predict acidity. Now you can also use ARIO to predict basicity. As we said before, you're stronger your acid, the weaker your conjugate base is. So it's basically the opposite effect. So in a nutshell, so it's just going to be completely opposite. The more stabilized the negative charge on the base is, the weaker that base is. So again, circling back to our first example, these two bases here, which one is more basic than the other? Notice that the first base has a negative charge on the oxygen versus the second one has a negative charge on the carbon. Which one is better at stabilizing that negative charge? That oxygen, right? That oxygen can more stabilize that negative charge. Remember, if it's stable, then it's quote unquote happy, therefore it's not going to want to react. Whereas something is less stable, then it's going to want to react. So in this case, the negative charge on that carbon is not very stable, so it will be more basic. So yes, so you can do the same thing with basicity, just the opposite. And when it comes to comparing basicity, you don't have to imagine the conjugate. You can just compare the base molecules as is.
All right, and the last thing I want to talk about here is to talk about how solvent can affect the pKa's, the acidity of your compound. We'll take a little example where ARIO will not help us to explain why one molecule has a higher pKa than another. An explanation, turns out, comes from the interaction of the molecule with the solvent.
A prime example of this is to compare tert-butanol and ethanol. Okay. They are both alcohols, so you would imagine them to have the same pKa's. But in fact, ethanol is 100 times more acidic than tert-butanol. And the reason behind this is the solvation effect. So as we draw in the conjugate base of both of these molecules, we want to see how its negative charge is being stabilized. Using ARIO, we can see no difference between these two molecules. However, notice that on the 2-butanol, there is a very bulky group next door. This bulky group blocks the solvent in accessing this negative charge. And once the solvent can't access this negative charge, it can't help stabilize it. Because the solvent molecule can have a positive end, it can interact with that negative charge, and with that interaction comes the stabilization. right? So imagine if we have a solvent molecule with its positive end sticking in towards the negative charge. In the tert-butanol, you can have space for maybe up to a few until you get blocked by that tert-butyl group. Whereas when you have more space around, you now have more space for solvents to come in and stabilize that negative charge. This effect is quite remarkable, giving the pKa of ethanol to be around 16, whereas the pKa of the tert-butanol to be 18, right? It's less stabilized because of that bulky group. The effect of the bulky group in this acid-base consideration will foreshadow other events we will talk about in this class. So this is a good introduction to it. When you have this bulky effect, we call this sterically hindered. And in essence, sterically hindered just means that it is blocking access in an actual physical space. All right, so that wraps up our discussion on acid-base chemistry for this chapter.